Another classic type of optimization problem is to minimize the amount of material costs that go into building some kind of shape. In this case, we're looking at an open-topped box. So this top is missing, but we have the four sides and the bottom included. We're also told that the length of its base has to be twice its width. So if we call this the width, this will be two widths this way. Now we also have a difference in cost. Material for the base is more expensive than material for the sides. So let's determine the cost of the material for the least expensive possible container, knowing that it has to contain 10 cubic meters when we're done. Okay, so what do we have in terms of relationships here? We know we need a volume of 10. So the volume must be 10, and that is equal to 2 W's times a W times the height. Let's put that on there. What else do we know? Well, we also know that there's going to be a cost to build that. And the cost is going to be $10 per square meter of the base. So let's do this in stages. It'll be the cost of the base plus the cost of the sides. And there is no top, so we don't have to worry about that. The cost of the base is going to be $10 per square meter times the size of the base, which is 2 W's in meters, times a W in meters. That gives us dollars. Good. Now plus the sides. Let's do the green sides here. Just add some labels. There's going to be the sides at the ends and the bigger sides here in the diagram. It's all going to be $6 per square meter for those, but we're going to have 6 times the two green sides. They're 2W by H. So if we want units again, this is dollar per square meter. That's meters. That's meters. And we're going to have 2 of those. So the 2W comes from the length of this side, and there's 2 of those sides, 2 green dots. And then we're also going to have the red dotted ones, which are going to be in meters. And meters, whoops, let me try that again without the linearization happening. Meters and meters of the W times H. And once again, there's going to be 2 of those, that side plus that side. So the cost of building the box will be 10 times the size of the base plus 6 times the 2 sides green dotted plus 2 times the area of the red dotted sides. And here it really does behoove us to simplify, because we're going to want to differentiate this later, and it'll be much easier if we simplify it now. What else do we have here? So we have 24 W times H plus 12 W times H, and that can be simplified down to 20W squared plus 36 W times H. So the cost is what we want to minimize. Minimize the cost while keeping the volume constant, while keeping the volume at 10 cubic meters. What that lets us do is get rid of one of these 2 variables. So far we have too many variables to differentiate, so what we can do is take this volume constraint and let's solve for H. We have lots of W's here, so let's solve for H. It'll be 10 over 2W squared, or 5 over W squared. Okay, we're almost now at the stage where we can do the derivatives. We just need to put this H into this formula here. We'll do that on the next page. Our cost is, I already forgot, 20W squared plus 36. 20W squared plus 36WH. Our H was 5 over W squared, so our cost can be rewritten as 36W times 5 over W squared. And we can simplify that one step further. 36 times 5 is 12 times 5 is 60, 180 over W. That's our cost. Okay, so we know based on the dimensions we pick, what the cost of building the box will be. We want to find the critical points of the cost. So we need, let's call that C. Let's find C prime then, and that will be 40W plus 180. This is W to the negative 1. So we're going to get negative 1 W to the negative 2 as our derivative. We're going to set that equal to 0. So 0 is equal to that. And let's rewrite that just a smidge while we're here. We can bring that over. 180 over W squared equals 40W. 180 over 40 equals W cubed. Okay, so 180 equals W cubed. W will equal the cube root of 180 over 40, or 18 over 4 if you like, or 9 over 2. And that's approximately 1.65 meters. All right. For those going into economics and biology, we'd often call this W star. It's the optimal value. We'll call it that just because it'll help make a nice landmark as we go through the next stage. So our only critical point is at that value. The only critical point of the cost is W star equals approximately 1.65 meters. Okay. Again, we have a few different things we could do about domain here. This time, why don't we treat it as if we have an open-ended domain, because we actually do. We can choose W to be as large as we want, because the H would just get smaller and smaller, but it would never get to 0. So we really do have an open domain. The domain is W bigger than 0 and less than infinity, which is an open domain. And if that's the case, it's easier to make the single critical point argument. So we have W, we have 0 here, we have the magic point, the critical point, 1.65, or W star here, and we had C prime, which was 40W minus 180. Minus 180 over W squared. In that scenario, again, as W gets bigger and bigger and bigger, this fraction gets smaller and smaller. So we're left with 40 times bigger numbers, all positive. So we're going to end up with a positive derivative here. So if we want to do a sine of C prime chart here, we're going to get positive values here. And imagine coming in from infinity, as W gets smaller and smaller, eventually this term is going to get big enough to cancel the previous term. That's when we have our critical point, or derivative 0. And then after that point, we're going to have a small number minus a bigger number, and we're going to have a negative critical point. So for all W less than that W star, the cost is decreasing. So in other words, when W is smaller, if I make it just a little bit bigger, I'll make the cost go down. So I keep getting the cost decreasing. And for all W's larger than that breakpoint, the cost increases. And the combination of those two things tells us that that W star 1.65 meters is a global min for the cost function. Okay, because we actually have the function going down, hitting a 0, and then going up, and it continues to do that right up to the boundaries of this open interval here. All right, last but not least, this is just one part of the design. So what are the whole dimensions? So we've convinced ourselves, I hope, that we found a global minimum. The question next is, what's the actual box we would build? How would we specify it? Well, the dimensions then would be W star 1.65 meters by 2 W stars, or 3.3 meters by H. And what was H? Let's go back. Way back here, H was 5 over W squared, and 5 over W squared is around 1.8 meters. And if we multiply this out, 1.6 times 3 is about 5 times about 2, we actually get a volume of 10. That's good. That's a check mark there. And the cost that goes with that is equal to, we can just use this formula because we found it earlier. Oh, that's our derivative. Let's not use the derivative. The cost that we have was 20 W squared plus 180 over W. Clean that. And if you get your calculator out for that with the value that we're using, 1.65 for W, we get about $163 for this box. Keep in mind, this is a huge box. This is 10 cubic meters, is quite large. And we get a cost here of $163 total.